All right, ladies and gentlemen, 20.9. This is it. We've been waiting a long time for this one. Back in 20.3, you learned everything about a voltaic cell. Now the question is, what's the difference between voltaic and electrolysis? Okay, so let's begin. Calculate the amount of charge flow based on the changes in the amounts of the reactants and products in that electrochemical cell. About the last equation you're going to be seeing. Faraday's law can be used to determine stoichiometry, yay, stoichiometry, of the redox reactions occurring in an electrochemical cell with respect to number of electrons, the mass of whatever material, aka chemical element, whatever it may be, from the electrode, the current, the time, and the charge. Now, you have this equation right here, okay? And what it helps you with, let me bring up the equation sheet, and right here. Yeah. Oops, sorry. Right here, the very end. Okay, notice it says capital I. I is called current in amps. Okay, I'm going to write that down. I is current, and capital A for amps. Okay, so A-M-P. Okay, it stands for amps. And then, ooh, I'm already losing my voice. Then it says Q. I know it's going to be like freaky when you see that Q. You're thinking heat. But in this topic, ladies and gentlemen, the Q is called charge, called coulombs. So Q is charge. And we're talking about the charge of the ionic species. So we're looking for an actual particular charge on a chemical. And that is right there. Let me go back to it. I want to make sure I write down what they have. Coulombs. So big C, Mr. Coulombs. And then you got T, obviously, for time. Now in this case, the time that we're going to be measuring is in seconds. Okay? So you have I over Q over T. So basically you have amps, capital A, amps, equals coulombs over seconds. Now this is going to be really important when we get to the very end. Okay? And then you're going to see how we're going to use this with stoichiometry. Okay, so first, and that should be the very last equation, ladies and gentlemen, that we've ever talked about. If you go through your equation sheet, there is not one equation we did not beat to death. Okay, I'm looking it over, and yep, we did them all. Okay, so with this I equation, I don't usually look at it this way. I usually just do it with stoichiometry, but I just want you to see where that I is coming from. So you got amps over amps equals coulombs over time, over seconds. Electrolysis versus voltaic. Okay. Electrolysis is not thermodynamically favored. Not. Is because of this. It requires help. It requires an outside source to make it happen. And it's right there. It's called a battery. And don't we know something about a battery? Voltaic cells are a battery. Voltaic cells are thermodynamically favored because they don't need help. Electrolysis does, and it requires that battery. It requires that circuit. Okay, Jose, you mentioned a circuit. It requires outside help to make it operate. So electrolysis, it uses electricity to bring about a chemical change. Literal transition of electrolysis means splitting of electricity. And they take place in what's called electrolytic cells. So why use electrolysis? Man, we use this stuff so much in our everyday life. Not us, but people out there in the industry. It's called like silverware, coins, jewelry. That's how they use electrolysis. It's basically to separate ores or to plate other metals onto other metals. And it's called electroplating. And in the book, it does talk about this in 20.7 and 8, but it's not on the AP test. But if anyone is actually interested in what's called electroplating, alloys, ores, and stuff like that, you may want to just take a little gander after the AP test, okay, of course. Silverware. Silverware is basically an example of electrolysis because it's where silver is plated on top of nickel. I mean, you're not eating with pure silver in your silverware, forks, spoons, and knives. You're actually eating with silver-coated metal. It's like the copper penny. The copper penny, the outside of it is copper, but the inside of it is zinc. And it's only about 3% of a penny is copper, where the other 95% is zinc. It's because copper is so expensive. We would have to change the value of a penny to at least 2 or 3 cents, and it's not that worth it. There's always been legislation out every year where somebody is trying to basically get rid of the penny and then just make the nickel as the lowest cents. Well, the problem is when you have things called 99 cents, or the McDonald's meals that used to be not a dollar meal, but used to be like the 99 cents or the 50 cent. And basically everything, ladies and gentlemen, would basically increase in price. Like gas is usually like $3.99. Well, there won't be not such a thing as $3.99. It'd either be $3.95 or $4. So you're thinking it's not much of a big deal, but it is when you get to like bigger items, like houses and cars and stuff like that. Everything would just become inflated in price. So that's why we still keep the penny, but just know that coins, jewelry, silverware, anything to that effect, there's an R, anything like that is an example of how electrolysis is used in life, okay? In a video, okay, Tyler DeWatt, the last video, okay, and I will show you where it's at. It's at the very end, okay, right here at the very end, electrolysis. That way you see the difference between voltaic cells and electrolysis, okay, because at the very end, what I'm about to do right now is talk to you about that difference. So I gave you a page, okay, and a lot of it's review. I understand, ladies and gentlemen, if you don't want to put some of the stuff on there, like oxidation numbers, how to figure them out, who's oxidized and reduced, it's all review. It's the electrolysis part of the video, and I don't remember what time it's at because he does it in the beginning, in the middle, and the end, but he does review in it too. I understand if you don't want to put that review in it, if you actually understand those concepts, okay, but make sure you get the electrolysis part in there. There are 4 big differences, big differences between voltaic cells and electrolytic cells, okay? Oxidation and reduction, okay? This is the part that's still the same, okay? Reduction will still happen at the cathode, and oxidation will still happen at the anode, okay? And the other similarity is electrons will still flow from anode to cathode. All right, that's good, okay? But with electrolytic versus voltaic, there are 4 big differences. Some people think maybe 5, but these are basically the big 4, okay? Number 1, we already know voltaic cells are spontaneous. I'm going to do like little color coding here. And electrolytic are not thermodynamically favored, is because you have to force it to happen, and you actually have to either use some type of electricity or use a battery source or a DC source. DC source is another type of battery. There are some, if you ever go to like a hardware store, there's like AC voltage versus DC voltage. It's way over my head. I just asked the husband to get me whichever one we need. But I just know that there is a big difference when it comes to what type of battery you can put in what things. Voltaic or spontaneous, electrolytic or not, okay? A voltaic is separated by 2 cells to generate electricity. So with voltaic, remember I told you, like, kind of think of it like, 2 little beakers, 2 little cells, and that way you have like the salt bridge that connects it to get the ions to migrate. But the problem is electrolytic. I always tell students, and Jose was asking me about this the other day, think of it like a giant fish tank where you have like this one electrode over here, your anode, and then one electrode over here, your cathode. That's it. There's no barrier. There's nothing in between it. So like think of it, like I said, like a giant fish tank where you put these 2 electrodes in it and then turn it on and see what happens. A voltaic cell is a battery. That's why we use batteries in pretty much everything we have out there in the world, because there is that positive and that negative. There is a current going in that battery. But an electrolytic cell, it needs a battery. So as you see in the picture, when we would have our electrodes for voltaic, and we just have a wire, that's all it is a wire, and then we hook it up to a voltmeter, but the purpose of that voltmeter is just to measure the volts. That's it. I mean, he's not part of the reaction. He's just what I need to measure the volts. But the problem is with this one, they usually put like these little kind of wavy lines to signify like a circuit. But this part right here is the battery. It needs a battery or it doesn't happen. In a voltaic cell, the anode is oxidized and the cathode reduction is positive. So over here, if this was my, let's say this is my anode over here, in a voltaic, the anode is negative. But over here, my cathode is positive. Okay, all right, because that makes sense, ladies and gentlemen, because to drive these electrons from anode to cathode, those electrons, negative, are attracted to the positive cathode. However, in the difference, okay, so voltaic, the anode is negative and the cathode is positive, okay? But the other big difference, this is why it's not thermodynamically favored, is the charges of the electrodes swap. In this case, your anode is positive and your cathode is negative. And you're probably thinking to yourself, what? How do the electrons still flow from anode to cathode? They still flow that way. It's because we force it to go that way. We force the reaction to happen, okay? So we have to actually hook up a circuit, a battery, some type of DC source to make those electrons flow still to the opposite side. I'm sorry, to the same side, the negative and the negative. Still make it flow from anode to cathode. That's the big, big difference between the two. Oops, hold on. All right, so this last part, ladies and gentlemen, let's see how we do a little bit of stoichiometry with this, okay? So quantitative aspect of electrolysis. So remember this equation that we just put up here, okay? This amps equals coulombs over seconds. All right, here we go. So remember, a Faraday, as we did in 20.6, a Faraday is a charge of 1 mole of an electron. And it has this charge of 96,485 coulombs, okay? Now we know, according to that equation on the equation sheet, an amp is 1 coulomb over seconds, okay? And we can even, if we wanted to, we can even rearrange the equation. 1 coulomb is amps times seconds, okay? So when you're doing these calculations, ladies and gentlemen, this is the one you get on the equation sheet, okay? They just don't say the A, the C, and the S. It says I, Q over T instead. A coulomb is the amount of charge passing a point in 1 second when the current is 1 amp. So they're measuring this charge that's passing through a period of time at 1 second at 1 amp. Okay? So let me show you how to use this. It's very simple, but I ain't gonna lie, ladies and gentlemen, it's a lot of steps. These are the type of stoichiometries that are long, sometimes up to 6 steps. Okay? All right, so let's say we have the following. I want to calculate grams of aluminum that are produced, and this is how I would be doing it on the AP test. When I'm reading the story, I'd be like circling stuff. Okay, I want grams of aluminum. I know time is 1 hour. Okay, and you don't have to. This is just me and my OCD of listing what I know and I don't know. Of this molten aluminum chloride, if the current is 10 amps. Okay, so I know amps is 10. I got to get to grams. And it's kind of like, let's do a roadmap. If I'm trying to get to grams, usually what happens is before grams, you would need moles of aluminum, okay? Because usually grams, moles, grams, they go hand in hand. But another step right before it, okay, remember right here, is a coulomb is the charge passing through a point 1 second per 1 amp. But remember what a Faraday is. It's a mole of electrons. So the step right before this, moles of electrons. And then it can lead us, and we can go backwards, we can go either way, okay? And then we have the quantity of charge. We have coulombs, okay? Mr. Coulombs. And remember what a coulomb is. It's the amps times seconds, okay? So that's what a coulomb is. Think of it like when we were doing our big stoichiometry chart and trying to figure out how many steps. This is kind of a big roadmap to help you get there, okay? I usually like to deal with time first. I like to get that out of the way because somehow, ladies and gentlemen, I got to get this time. I got to get it into seconds, okay? And then I have these amps, okay? I'm going to need to get these amps into coulombs, okay? Because then I can use coulombs over seconds, or I can go amps times seconds, but basically I'm trying to get to this coulombs. So then I can use my roadmap to get there, all right? So a coulomb is, let's start with big C. A coulomb is, and we will definitely practice these in class, amps times seconds, okay? And now what do I know? I got the amps part, but I don't have the seconds. So this is why I usually like to tackle the time first. So for time, I have 1 hour, and I got to get to seconds, okay? Now, ladies and gentlemen, not rocket science. 1 hour. And if you're thinking 360 seconds, we got some big trouble, okay? 3,600 seconds, just go straight to seconds. And obviously it's the same value. Now we did start with 3 sig figs. We got to keep the 3 sig figs. This right here, this is what's called a constant, 2 sig figs. You can even go 2 sig figs. But you're going to have that 3,600 seconds. And you can put it in scientific notation if you wanted to, but really didn't need to. And actually, I think yeah, 1 hour. Yeah, never mind. I was thinking it was 10 hours. Okay, so 3,600. So I got my amps. My amps was 10.0 amps. And let me show you what an amp breaks down into. See this amps right here? This 10.0 amps equals a coulomb over seconds, okay? Because I got to get to coulombs, so then I can start my roadmap, okay? So 10 amps equals, and amps is coulomb over seconds, so it's the same thing as me saying 10 coulombs over seconds. And now if I multiply by that seconds, and you don't need anything under it, you can just call it 1. That's how the seconds cancel. So when I multiply that together, then obviously the number just gets bigger. So 36,000 big C, big coulombs. Okay? So hopefully with me so far. And now let's go to the grams. So coulombs, at 3,600 coulombs. And there's where Mr. Faraday comes in. Okay? Remember a coulomb, right there, is a mole of electrons. So that 36, sorry, not 36. Faraday, the 96, 485, big C. And a Faraday is a mole of electrons. Now, we put that 1 mole of electrons. I've even seen students put 1F, capital F, and that's okay. It's either one, okay, whichever one you want to put in there. And now that gets me rid of this. So now I'm here, moles of electrons. Now how am I going to use this moles of electron? How the heck am I going to get rid of the electron part so I can get to aluminum? Well, let's look at what happened in the story. I have aluminum chloride. And if I go old school, ladies and gentlemen, if you had to tell me what was the charge of that aluminum, well, go backwards. Chlorine's -1, according to the periodic table. And aluminum doesn't change on the periodic table. He's +3. And how many electrons were involved in this reaction? Well, he lost 3 electrons to give them to chlorine. So that's the moles of electron. So now that I have my mole of electron, I got to get rid of the electron part. So I put mole of electrons, and now I can get to Mr. Aluminum. Mole of aluminum. Now we know there's 3 electrons that were involved, and those 3 electrons we lost. So we lost 3 electrons for every 1 mole of aluminum. For every 1 aluminum, we lost 3. Okay? So bye-bye, Mr. Electron. Here comes aluminum. Now basic chemistry, ladies and gentlemen, now get to grams. 1 mole of aluminum. And then according to our periodic table, it's like 27 something. I don't even have a periodic table in front of me. Give me a second. All right, how to look at my periodic table. 26, I think that's 98. My gosh, that is like so small. 26, 98, okay. It was 27. Sorry, all my stuff is at school now that we're back at school. 26, 98 grams, okay? So bye-bye, Mr. Mole. And here comes grams. And now simply plug in. Now, ladies and gentlemen, you do have 2 numbers on the bottom that needed to be divided. Okay, so multiply these first, and then divide, and then divide. Okay, so 3,600 multiply 26.98. Okay, and you get about 97,000. And then divide 96,485. And then hit divide again, 3. And you should get a small number. And I want to make sure I did. Oh, I knew I forgot a 0. I was like, wait a minute, I'm off by 10. Oops, sorry. 36,000. See, Joel, you couldn't correct me now. 36,000. Let me plug that in one more time. And then multiply 26.98. Divide 96,485. Divide 3. All right, there it is. I knew it was like 3 something. 3.36 grams of aluminum are needed to produce an ampage of 10 amps in 1 hour. Okay, that's the calculation you need. So think of this roadmap, ladies and gentlemen. It will help you with whether you have to go to coulombs or amps or go to grams or moles. It will help you get there. Okay, I did bring in 2 more examples because this is the type of equation, ladies and gentlemen, that you just need to practice it. Okay, it's not difficult. It's trying to remember what a coulomb equals to an amp or what an amp equals to a coulomb. Okay, so 91 right here. And this is usually a homework question, but I wanted to get you some more examples. So right here. All right, let's tackle this one. We have chromium 3. And it looks like there was a loss of 3 electrons. And I'm doing exactly, if I was taking the AP test, what I'd be doing. Using a current of 7.6 amps. I want to find mass that is plated over 2 days. So I know time, I know amps, and I want to find mass. And it's kind of like what we just did up above. But then I gave you another one where we're going to find amps. Okay, so right up here, we got our roadmap right there. So I want to tackle these days because I can't use days. I got to get to seconds. All right, so what do we know? In 1 day, there is 24 hours. And in 1 hour, we have 3,600 seconds. Okay, so by days and hours. So I'm going to get 2 times 24 and then times 3,600. And I'm going to get a big number. And with sig figs 2, we'll go 107,000 seconds. Okay, that's a lot of seconds. And now let's use our coulombs equals A times S. So coulomb equals amps times seconds. And our amps was 7.60 big A. And if we, remember, convert that amps into coulombs, 7.60 big C over S. Okay, and that right there, that helps you with this. A equals Q over T. Amps, coulombs, seconds. Okay, and now we're going to get rid of those seconds. 170,000 by seconds. So 170,000 times 7.60. Even bigger number, 2 sig figs. It says 129. You can round it if you choose. 1, 2, 1, 2, 3. Yep, 1,300,000, and that's big C. So now we have big C. Big C. And then we are going to use Mr. Faraday. 96,485 big C. And that equals 1 mole of electron. Or you could say 1 Faraday. And by big C, here comes how many electrons were involved. Well, I had chromium plus 3, so that means I lost 3 electrons. So 3 moles of electrons for every 1 chromium. So bye-bye electron. And now we're going to look at Mr. Periodic Table for chromium. For every 1 mole of chromium, chromium is 52 grams. And now I got rid of moles. So if I take that 1,300,000, and I'm going to multiply by 52 and divide by 96,485, and then divide again by 3, I get 234 grams. Now, if you had not have rounded this 100 and kept it 120,000,000, you probably get about 236, but it's only because of those sig figs. It kind of always screws things up. So don't forget the chromium at the end because we are talking about a chemical. Okay? All right, part B. I want you to try part B. Okay? We want amps. So in the end, we want capital A. That's plated when you have 0.250 moles of chromium. So I don't need to get to grams. I'm just going to start with those moles. And I still lost 3 electrons. And I have a time of 8 hours. So you know, let me get you a little head start. You know we have hours. I've always done hours as HR, but you can also do H. And in 1 hour, 3,600 seconds. So 8 times 3,600. And let's see, 2 sig figs, it's 2,880, so we can go 29,000. Like I said, you can also keep it 28,000, okay? And now you got your seconds. I got to get to amps. And somewhere in here, I lost my 3 electrons, okay? So instead of starting at grams, start at moles. 0.250 moles of chromium and work backwards, okay? Get to moles of electrons, get to coulombs, and then use this guy. You got seconds. You're going to, as soon as you get to here, you're going to have big C. You plug it in to solve for A. Let's see what you get. Now, if you do this right, ladies and gentlemen, you should get 2.51 if you do this right. Ladies and gentlemen, that was our last recording. And as much as I am thankful that it's the last one, after I can't even tell you how many videos that I've made. I think it's at 140 something. But I am beyond proud of you. And I will keep fighting with you these last 2.5 weeks until we get to the AP test. And the more we practice, the stronger we get. So I need you to continue to fight. You've got to continue to fight, because if you don't fight for this one chance, ladies and gentlemen,